So hello everyone, welcome back to the channel. So welcome to the post-contest discussion of the Codeforces round 997, which was rated for the division 2, 3 and 4 people. So actually I had a rough contest today. So let me refresh the page. Okay, system testing is going on. Actually I solved 3, I believe. So yes, let us take a look at the solutions. Okay, A was already up anyways. So there is m by n square stamp. So basically there are timestamps in the description, okay, or below the video automatically. So for those who have understood the question well, can directly skip to the solution of the problem. Okay, so there is m by n square stamp on an infinite piece of paper. So initially bottom left corner of the square stamp is aligned with the bottom left corner of this paper. So uh, instead of reading the question, let me briefly describe it to you. So there will be this one square at this position. So see here, this is the pointer. Keep the track of this pointer. Okay, so your square bottom left corner will be right here, and it is of length m. Here m is equal to 3, so it will be till here, right, till here. So this will basically be our square. Okay, so in the first step you are moving it to the right and moving it up. Okay, so this will be the state of the square, and in second step you are moving it to two units to the right and 2 units to the left. Then this red square will be the will be the position of our stamp, and you are enclosing the part of the stamp which is where it to till we made, right. So basically you can uh, connect these two figures. So basically you are excluding these parts. So yes, these parts. Okay, so that is the thing. And yes, to find the perimeter, you can notice that I can take this image. So let me draw it here. So let us suppose this is the final. Okay, this is the our final state of our thing that we have created. Okay, so yes, I can always take this edge. Okay, I want to count the perimeter, means I want to count the sum of all these lengths, right? All these lengths. Okay, so to calculate that, basically what I will do is that I will form one imaginary rectangle right here, right at the boundaries. Okay, right at the boundaries, and I will I will what you can say, I will take this part, this line left till here. Okay, so it will be like this. Similarly, I will take this line to the left till here, it will be like this. Okay, and I will take this line here, it will be like this, and I will take this line right here and it will be like this. Similarly, I'll do it for the horizontal lines. Okay, so take it upwards, take this thing upwards. So I think you are basically getting the idea of the solution, right? So it was a pretty easy problem. Okay, so not so easy for, I think, the beginners, I would say. So yes, and we will erase all these parts. Okay, so we will erase these things. Okay, these things. Okay, so basically after erasing all the things, all these lines which are in the rectangle, you can see that the perimeter of the rectangle is just this thing, right? So right, and that was basically the solution. So yes, I can show you the code. So there was not much in this problem, I would say. So this is taking the input for the first step and initializing our x, okay, initializing our x and initializing our y, and then for n minus 1 step taking the input and adding it to the x and y accordingly. Y is for the height and x is for the length, and yes, outputting accordingly. So think there was nothing much to be done in this problem. So why this minus p and minus q? So basically it was for these things. Okay, so follow this pointer. Okay, so coming right here, so it was basically doing minus for this thing. Okay, this length and this length from the total length and height of the rectangle, you can say. Okay, so yes, that was basically the easy solution for A. Let us head towards the solution of B. Okay, so B is a pretty nice problem, I would say. So uh, I will not try to give the intro of the problem, but to rather explain it briefly. So basically you are given the adjacency matrix, you are given the adjacency matrix representing the edges, and you want to find the permutation holding this condition. Okay, holding this condition. Okay, I would recommend you to completely or neatly read the problem statement once again. It is not that complicated. Okay, so yes, let us take a look at this sample test case. Okay, this is basically a really nice sample test case that they have provided. Okay, so we lost it. Okay, not, we have not lost our whiteboard, it seems. So yes, for this solution of this problem, what we are going to do is that, so listen, so this is our given test case. Okay, so what I can notice here is that, so focus on the position of 5. Okay, focus on the position of 5. Okay, so what I can see is that there exists edge between all the elements and 5, right? So basically there is nothing on the right of 5. Right of 5. Okay, makes sense. Yes. So basically these are our positions in the answer array. So basically there's nothing on the right of 5. So 5 is the rightmost element. So let us climb up in our matrix. So consider this row. Okay, so this row is the fourth row. Okay, so it represents edges going in and out from the vertex 4. So taking a look at this 1 2 3, so first column, second column and third column. Okay, so what I can notice is that if its value is 0, so for values less than 4, which are 1 comma 2 comma 3, if there doesn't exist a edge between these values and the 4, so they all are right of the 4, right? They are all in the right of the 4, right? So to the right of 4, to the right of 4, there are three elements. Hang with me. So there are three elements which are basically 1 2 3, and check this thing also. So after this diagonal element, check this one. Okay, so 1 means that 5 is on the right of the array, right of the 4, right? So because there exists h in between 4 and 5, and 4 is less than 5, so basically 5 is on the right of the 4. So cumulatively to the right of 4 there are 4 elements. Okay, makes sense. So to the right of 4 there are 4 elements, so 4 must be here. Makes sense? Yes, absolutely does. So let us climb up in the matrix. Okay, so this thing. So let us check the values 1 comma 2. As we are checking for the third row, let's check the values 1 comma 2. Okay, makes sense. So it is 1 and 1. So basically there exists edge between 1 comma 3 and 2 comma 3. So 1 and 2 must be on the left of 3, right? Must be on the left of 3. Yes, yes, true. Yes, so uh, till now there are 0 elements to the right of the 3. Okay, so let us check for this 4 and 5. So there exists a edge between 3 and 5. So 5 must be to the right of 3, right? So doing +1. And taking a look at this 4, there doesn't exist edge between 3 and 4, so 4 is to the left of the 3. So here you can notice there is only one element to the right of the 3, so 3 must be here. Makes sense? Yes, definitely does. And similarly, checking for 2, checking for the second row, checking for the second row, so we'll check if there is edge between 1 and 2. Is there any edge between 1 and 2? No, there is not. So 2 is basically to the left of 1, right? Okay, wait. 2 is basically to the left of 1. So there is one element to the left of 2, and then check for 3, 4 and 5. So there is edge between 2 and 3 and 2 and 5. So basically they both are to the right of the 2. So to the right of the 2 there are 3 elements. Yes, so to the right of the 2 there are 3 elements, so 2 should fit in here. Okay, so and you can also check for the first row, you'll get there are 2 elements in the right of the 1. Okay, makes sense? Yes, absolutely does. So this is our final answer. So you have to iterate through every row and check how many elements are present at the right of that element. Okay, so solution will go like iterate over every row, check how many elements are to the right of the ith element. Okay, makes sense? Yes, and this is when you are checking ith row, right? For the ith row. And so for our test case, it was like for 1 there were 2 elements in the right, for 2 there were 3 elements in the right, for 3 there was 1 element in the right, for 4 there were 4 elements in the right, and for 5 there were 0 elements in the right. So when you have calculated this array, when you have calculated this array, one more thing remains is that, so there are two elements to the right of 1, so one's position, so let us create an array for the positions. So one's position is n minus 2, basically 3. So 2's position is 5 minus 3, 2. 3's position is 4. Basically, it is 5 minus 1. And 4's position is 5 minus 4, which will be 1. And 5's position is 5 minus 0, which is 5. So basically, you get the positions of the every element. Okay, so that is what all we want, right? Yes, so let me head you towards the code. And one more insight here is that, so when you check the number of permutations possible from 1 to n, if you have numbers from 1 to n, it is n factorial, right? It is n factorial. Makes sense? So, but when you check the number of graphs possible, so when you check the number of graphs possible on the n vertices, you'll get 2 to the power of nc2. Why 2 to the power of nc2? Basically, there are nc2 means n choose 2, which is n into n minus 1 by 2 edges, and you can select that edge in the graph or neglect that edge in the graph. So basically, for every edge, you have two choices, and the number of edges is nc2, so that's why your number of graphs possible will be 2 to the power of nc2. And you will notice that this n factorial is always less than or equal to, not equal to. Basically, equality only holds for maybe some 1 2 elements for 1 to n, but it is generally bigger. Okay, so for most of the cases, n factorial is greater than 2 to the power of nc2. So what we noticed here is that, so for many graphs, okay, so for many graphs there doesn't exist any permutation. For many graphs there doesn't exist any of the permutation, but in the question they have given that it is it is guaranteed that there exists a permutation p which generates the given graph. It is also guaranteed that graph is undirected and has no self loops. Okay, but main part here is that it is guaranteed that there exists a permutation p which generates the given graph. Okay, makes sense? Yes, absolutely does. So we don't have to care much about this mathematical fact. Okay, we can just proceed to write the solution. Okay, so yes, just taking the input and basically doing the same thing that I have explained in the solution. And yes, here is one important manipulation. So after calculating the indices of the array, so after calculating the positions of the array, so basically here, you are here after the for loop. So for every edge you are here, so you know the position of the every element, so you have to reverse it, right? You have to reverse it. At position 3 you want to print 1, at position 2 you want to print 2, at position 4 you want to print 3. So that's why this store vector is just reversing the things, right? It is reversing the pair element comma position to position comma element. Okay, makes sense? Yes, absolutely does. So that's the pretty short solution and pretty nice. Problem was actually nice. So yes, let us head towards the problem C. Okay, let's check if C got accepted. Yes, it did get accepted. So C was also pretty annoying question, I would say. But it has a really a simple construction. Okay, it is what you can say, 2 minutes of thought, or whatever you want to say it, but it is really easy question, man. I thought B was harder than C. Okay, so I think B was harder than C, so let's check. So I would just tell you the construction, how it works. So basically what you will do here is that at first position you'll take one, at the last position you'll take one. Okay, so sorry, okay, the second position you'll take one, and also at the last position you'll take one, and all the other positions in the array you'll fill with 2, 3, 4, so on up to whatever it is. It will be n minus 3, I believe. Yes, because there are, okay, not n minus 3 actually, so it will be n minus 2 till n minus 2, because there are two extra ones here and they will occupy the elements position of the for the elements n minus 1 comma n, right? So they are just counter for these elements. So anyways, so this is just basically the simple construction you need. So for n is equal to 6, see here, so 1 2 3 4 5 6, so 1 1 1 2 3 4. So notice here that you have f of a is 3 here. So basically 3 is the length of the largest palindromic subsequence possible in this array, and the combinations are 1 comma 1 comma 1. This is the first initial combination, and others are, yes, let's hop, 1 2 1, and then this 1 3 1, and then this 1 4 1, and then this 1 2 1, then this 1 3 1, and then this 1 4 1. So basically there are 6 other possible combinations, and this one combination for 1 1 and 1, it will basically give you 7. So for 6, g of a is basically greater than 6, which is 7. Makes sense? Yes. And you can verify that, suppose there are, so here n minus 3 elements would be fit here, right? So n minus 3 into 2, for this one, there will be n minus 3 such subsequences. For this one there will be n minus 3 such subsequences, so that's why n minus 3 into 2 plus one subsequence for this once. Okay, makes sense? Yes, it absolutely does. So your ultimate answer is like 2n minus 5, right? So notice here that cleverly they started n from 6. Okay, cleverly they started n from 6. So if you plug in 6 in this formula, you'll get okay, so if you plug in 5 in this formula, you will get 5. So which is basically not greater than 5, right? Which is not basically greater than 5. But if you start from the 6, you'll notice that it is 7. So which is basically greater than 6. If you plug 8, if you plug 7, it will return you 9, which is basically greater than 7. So for every value, for every n greater than or equal to 6, this type of construction is valid. And yes, n starts from 6, n starts from 6. So yes, that is all from my side on this contest discussion. So pretty IQ related or ad hoc concept, pretty ad hoc contest, I would say. So I enjoyed solving the contest. I hope you did as well. So thank you for watching the post contest discussion on our channel. I really appreciate if you are watching till the end. And yes, see you again.